All right, now DES Part 2. Okay, this is a short one. Okay, we know what DES is. It was based on the Lucifer algorithm. It was submitted as a standard in 1974. NSA approved it in 1977. It says the original one used a 48 to 128-bit key. They decided on 56-bit. Okay. And 8 of those bits are used for parity, which is bad, which means it's even less. Okay. It says Lucifer was altered and called DEA for the data encryption algorithm. Okay. They determined need for protection-sensitive data during the 1960s and implemented the cryptography program in 1970. Okay. They invited vendors to submit techniques. This is where IBM submitted this. Did anyone mess with IE6 when they first enabled encryption? And you could only download it in the United States, and you had to sign. I checked that I will not export this to any foreign country. Does anyone remember that? Well, because they didn't want to make it so strong. Okay, and they were saying IIS6 supported encryption that if it was used outside the United States, it would be too strong. In other words, they wouldn't be able to break it, I guess. I don't know. Okay. So IBM had already been developing stuff for financial data. So they submitted it in 1974 and was accepted. Okay. There's controversy over it. Let me go back a slide here real quick. Because if you notice, it can handle between a 48 and 128-bit key right here. So if it can handle that, why didn't we go with that? Because they think they weakened it. That's what people are saying. They weakened it because it could have been better and they didn't. Okay. All right. Became a national standard in 1977 and an ANSI standard in 1978. All right. It was implemented in a majority of the commercial products and is actually still out there today. It's being used as triple DES. Okay. It was tested and approved as one of the strongest and most efficient cryptographic algorithms at that time, which makes sense. We're always getting better. You know, AES is the current top dog. Do you think it's going to stay that way forever? But it is currently. I mean, it might. I don't know. Okay. Okay, it's a block symmetric algorithm. 64 bits are put through 16 rounds of transposition and substitution ciphers. The order and types are dictated by the key value, because the key shifts. Then government uses it to protect sensitive by unclassified data. It's not for top secret data. And I mentioned somewhere, it was funny, I mentioned in somewhere I was speaking in Lawton, I think. And I mentioned top secret at some point. And some guy from goes, ever see that? Okay, well, I wasn't talking about this, I was talking about something else. He's like, you could never mention that. Okay, I guess that's a bad word. I don't know. Okay, so yeah, it was really meant for unclassified data. Okay, there's block mode. We're going to do some of these. We're going to do some more of these next class here. We have ECB mode, electronic codebook mode. So the same ciphertext is always produced for the same plain text. So if I take this piece of paper and encrypt it, it's always going to produce the same output. Understand? So the same ciphertext is produced by the same plain text. Okay. Very easy to identify patterns because I can change my plain text to see what happens in my ciphertext. Make sense? Okay. It's good with small amounts of data. If you're trying to do a whole bunch, it'd be very hard to work with. Okay. Each key indicates a different code book, and it's not important you know what that at this point, but keys kind of tell it which book to use, basically what it is. Okay, and it uses mesh authentication code for integrity and authentication. Don't need to worry about that, but it does. All right, here we go. So we have our plain text. We run it through our encryption with our key, and we get ciphertext. It's always the same. So the same plain text run through the same algorithm is going to give it the same encryption. Is that good? I mean, it's good. It does. And that's pretty much what the Caesar cipher is, if you think about it. The same plain text run through the same algorithm and the same output. That's part of the reason if you watch that movie, they were able to break it. It's because there was always specific words, what Heil Hitler and the weather, that never changed. They were able to use it to break it. Not the best plan. Okay? Okay, there's also cipher block chaining. It says encryption is dependent on the values from the previous block. So what we're doing is we're taking other data, encrypting it with it. So encrypt 64 bits, but chains them together by XORing them. Okay? So it's more randomized. Let's look at a picture of this one. So now we take something to start with, and we XOR that with our plain text. Then we encrypt that, and that becomes our ciphertext. Okay? The first ciphertext actually gets XORed with the next plain text. So even if we were encrypting the same exact plain text each time, it would not be the same ciphertext, because the prior ciphertext gets XORed with the next plain text. Make sense? Someone should be in there, Jim. Should be. Okay. All right. Decryption. You take your ciphertext, decrypt it, then XOR that with your initialization vector to get your plain text, and so on and so forth. Okay. So you think this is better than ECB? That's definitely more random. Definitely more random. All right. That is the end of the second slides.